Two universities, the University of Peradeniya, Sri Lanka, and the University Technology of Sydney, Australia, collaboratively develop an elephant-train collision prevention system to be used in the north-central province of the Sri Lankan railway network. The motivation behind this project is the rising human-elephant conflict. Human-elephant conflict has been a serious issue in Sri Lanka for past few decades. First 10 months of 2019, 93 human and 293 elephants have already been killed in the conflict, compared to 96 humans and 319 elephants for the whole of 2018. Electric fences, alarm systems have been introduced and implemented, but doesn't seem to have worked as expected. Even though several actions were taken to resolve, still a rapid increase of deaths of both human and elephants can be observed during the past 5 years. According to the statistics, the numbers keep growing annually. As a result of elephant attacks, especially in the north-central province of the Sri Lanka, most of the farmers lose their cultivations as well as homes. This has become a serious problem in the north-central province as many of the villagers are farmers. These wild elephants are strong enough to ruin cultivation spreading over acres over one night, and the farmers sometimes have to pay in their lives when they try to chase the elephant. There is a single elephant as shown in the pictures and is called Thanialiya in the local language Sinhalese. Villagers are scared even to hear the word Thanialiya because they know how cruel it could be and the dangerous consequences of its arrival. Generally, young elephants become Thanialiya as a result of its spouse faces an untimely death caused by an accident or subjected to shooting, especially the taskers. One of the most frequent accidents is hitting on the trains while traveling seeking water in the nearby lakes or on their return from water. Other than shooting by tusk hunters, falling in traps, one of the most common and most frequent type of accidents is the collision with trains, which passes beside the elephant corridor. In most of the time, the jungle or the park is on one side of the railway and the lake or the source of water is on the other side of the railway track. The elephants used to cross the railway track searching for water or food, and very frequently this is the time that they hit the trains. In the past 5 years more than 100 collisions have been reported resulting in injuries and more than 52 deaths to elephants as well as significant disruption to rail services. In Sri Lanka, there are approximately 1,508 kilometers of total train tracks and 280 kilometers of that travel through regions of high elephant population. According to the train drivers' feedback, the biggest barrier to avoid such collisions is the lack of visibility, especially in the dawn and in the dusk. This is mainly because of the train headlights only provide a sufficient visibility up to 300 meters, and it is an insufficient distance for a train driver to safely stop a train running typically at 80 kilometers per hour. Here are some news articles on online newspapers, reporting elephant accidents in the train lines. It is with this background and motivation we started the project. The project started February 2020. Initially, after the literature study and sensor data collection, the sensor unit was developed to detect the elephants. It comprises of infrared camera with data storing capability. In addition, it has the capability to process the video data and send the processed information to a remote location using the mobile telecommunication network. There are 2 remote locations, one in the nearby railway station to the hotspot of elephants, and the engine console of the train. In the long term, it is planned to use solar energy to power the sensor units, while for initial data collection process, it is powered with a high-capacity battery. Due to COVID-19 pandemic, there were delays in obtaining the required hardware. In addition, some hardware were not shipping to Sri Lanka. Therefore, alternative methods were used to obtain them third-party, and they were some of the reasons to incur delays in certain activities of the Gantt chart given in this slide. However, despite the rapid spread of the COVID-19, our team has successfully collected elephant data initially on tamed elephants and later on actual wild elephants in the jungles in the north-central province of Sri Lanka. The operations in the jungle were done in coordination with the Department of Wildlife Conservation in Sri Lanka and the Sri Lanka Railway Department. As you may imagine, it is quite a challenging task to collect data of wild elephants in the jungles. We have put tremendous effort and collected a reasonable amount of data which is sufficient to start training the convolution neural network-based elephant detection algorithms. Currently, that work is in progress, and once finished, we hope to transfer them to the onboard computer in the sensor unit, which will be fixed at elephant hotspots. Since the elephants don't like foreign objects in their sight, we plan to erect the sensor units on top of tall and strong trees which will be out of reach from elephants. As the initial step, a field visit was made to Palu Gasvawa area, which is located in the north-central province and is close to Habarana. In this area, there are long and straight railway tracks where many elephant train collisions have been reported. The main objective of this visit is to identify possible hotspots to locate the sensor unit for data collection. According to a train driver interviewed, who has over 7 years of experience in the same railway track which named Galoit-Trincomalee line, it is a 15-kilometer stretch where most of the accidents have taken place, and he has identified 6 hotspot areas where the elephants cross the track most of the time. We investigated all those 6 places and identified a suitable location for our initial data collection and tests. Identified hotspot were located close to 120 km milepost in the Ambepusa-Trincomalee highway and 133 miles along the railway line. All these hotspots were located in the Habarana jungle where a lot of train elephant accidents take place. Reolink, or IROS2020 camera module is used to capture the videos of the elephants. It has 6 infrared LEDs which enables a super long distance night vision up to 60 meters in low light conditions. The camera module is 12 VDC powered. There are Ethernet and Wi-Fi connections for data transmission. It comes with a default software interface for laptops called Reolink Client, and the same software can be used to operate camera from remote as well. Operations such as setting the camera angles, changing the recording qualities, etc., can be performed from remote. YOLO is an algorithm which used for object detection, and it is based on convolutional neural network known as CNN. It is very commonly used as a powerful algorithm for object detection. The transfer learning method was used to train the algorithm. Model was trained using the YOLO pre-trained weights and images taken using the sensor module. After collecting both daytime and nighttime data of the elephants, the algorithm training was started. In order to make sure the hardware is in order, a trial data collection was carried out before going to the hotspots in the jungle. The initial data collection was carried out in the Palakali Elephant House under controlled environment. These elephants are used in the annual procession in the Noble Temple of the Tooth in Kandy, Sri Lanka. During this trial, the power consumption of the sensor module and storage capacity of the sensor module were tested under real working conditions. Especially the behavior of the camera during the daytime as well as the nighttime was tested. The camera sensor module was mounted in of the hotspots inside the Habarana forest for data collection. In there, it was mounted on an existing tree and a signal pole used for signaling purposes by the Sri Lanka Railway. This was to make sure we do not show any foreign objects to elephants, as otherwise there is a high probability that such objects will be destroyed by them. After mounting the camera at the hotspot, both daytime and nighttime video data were recorded. Data were recorded nearly for 7 days. For the training process of the YOLO model, it needs images of different angles, distances and sizes of the wild elephants. To collect such images, we took special permission from the Wildlife Conservation Department and recorded both daytime and nighttime data in the Kadula National Park in Habarana, Sri Lanka, which is a site in the vicinity of the railway track. These are some of the pictures taken during the data collection process. In this visit, we identified several elephant passes across the railway tracks. Also, the maintenance staff of the railway tracks informed us that several elephant train accidents took place during last few years in that area. Apparently, these elephant passes connect the 2 jungles, namely Minariaya and Kadula, and hence the railway track is in between the 2 jungles. Elephants move time to time between these 2 natural forests for their food and most frequently for water. We develop an Android application for the train interface. This application features real-time interaction with cameras along the rail track which alerts the train driver about elephants crossing the railway track. provides real-time navigation data to the nearby stations and other information such as speed, any issues with the railway track, etc. Application can display live video feeds from the camera modules in the sensor unit, which are stations through the rail track. Development of the mobile application is almost started. Communication network between the sensor unit and the console panel is designed based on mobile GSM. Here, the algorithm in the console panel in the near railway station will request battery level status and camera connectivity details from the hotspot sensor unit regularly. Once an elephant detected, the alert message will be sent to the console panel in the railway station as well as to the console mobile application, which is visible to the train driver. Total power requirement of the hotspot setup was calculated and design a power supply for the system. All the equipment will be powered by deep cycle lead-acid battery pack. Solar PV panel and the charging unit will be used to charge the battery pack. We were able to achieve some results of the algorithm by using the data collected in different places. Intermediate outputs of the detection algorithm were obtained by using the data set collected at Pallekali. The algorithm can detect elephants during both daytime and nighttime. Especially when the environment is very dark, the algorithm was able to detect the elephant with 60% confidence interval. These results were obtained by using the initial data set which was collected in the Pallekali. The skin color of Pallekali elephants is very different to the wild elephants in the jungle. The focus of the preliminary tests with the YOLO object detection framework was to confirm that reliable results can be obtained for low-light infrared images. Thus the initial training was focused heavily on data from night scenes. However, these initial weights also provide reasonable daytime results. As these preliminary results were successful, we are currently in the process of expanding the training data set to reflect both daytime and nighttime scenes using data collected in the field supplemented with web-based data. After collecting the data around the hotspot, the algorithm was trained by using those data as well. Although there is a significant skin color difference between wild elephants and the elephants in Pallekali, the algorithm was able to detect wild elephants also successfully despite very low light conditions. All the testing of the algorithm was carried out in offline using laptop computers containing graphical processor units. Now the challenge is to transfer the trained algorithm to the single board computer with the sensor unit, which is Intel board, for the time being. The next step is to implement the algorithm in the single board computer with the sensor unit and test it within the real-time conditions. Finalize the mobile application cum console panel. Implementation of the communication network. Thank you.